The America's Cup is an amazing competition. It's the mix between the best sailors and the best boats. We've prepared a series of videos where we're going to design an AC-75 boat. Different parts, the foils, the hull, the sails, all with the tools we have in TakeOff Technologies. And I hope you're going to enjoy these videos and in some way they're going to be useful for you. Today, for this first video, I've chosen a pretty nice place. This place was where I was working during the COVID confinement, working with American Magic and spending so many hours here designing the foils that we had in New Zealand. So it's a little part of me that you have here. In this first video, we're going to focus on the section of the foil. This geometry is quite important because it's a big driver in the performance of the foil in terms of cavitation and drag. The first thing that we have to do is to set up the sailing conditions that we're going to have on the boat. First of all, we know the weight of the boat. The weight has changed during the 3 different America's Cup with this class of boats, but we're going to take as a reference the weight of 7 tons. Why do we take the weight of 7 tons? Because this is the weight that the foils will have to lift. So we're going to take it as a reference. And the other ones that we will need to know to define the shape of the sections is the speed at which the foil has to go. With these values, we're going to be able to calculate the main parameters of the section definition. We're going to make these videos as easy as possible. So if you need to define or design a section for any other kind of foils, you could use the same methodology. So we're going to go here in Tools and Fluid Calculations. Here on top, we have some parameters, really easy parameters, that will help us to define at which conditions the foil will be working at. So in this case, we even have an AC-75 foil. So we have velocity, we're putting it in knots, so we are more familiar with it. We're going to put a chord, let's put 0.3. The surface, we've put 1.4 square meters. Then you can play with these parameters. And then the lift we have to produce with this foil of 7.65 tons. We can reduce a little bit the surface, we can play with all these kind of parameters. And what is this gonna give us? This is gonna give us 3 very important parameters. So if you're not very familiar with aerodynamics, I'm gonna give you a little description of them. One of them is the CL. The CL is the lift non-dimensional parameter. What does that mean? You can produce lift. First of all, to produce lift, you need to have a fluid that have a certain density. The higher the density, the higher the lift. That's why we need very small surfaces into the water compared to the air, because the water has almost 1,000 times more density than the air. So it can produce 1,000 times more lift than the air. Then you need speed, and the speed goes to the square. That means if you go twice as fast, you will produce 4 times more lift. And then you need a surface. The bigger the surface, the bigger the lift. But then, even if you have the same density, the same speed, and the same surface, depending on the geometry that you have of the foil and the angle of attack, you will have different lift. And this angle of attack and geometries give you this CL value. It's a way to be able to compare very different types of engines like aircraft, foils, Formula 1 ailerons or whatever, and give a parameter that gives us an understanding on how much lift it's generating. For you to have an idea, here we have a little scale. The normal range of a CL that's lifting is between 0.1 and 0.8. What we consider a high CL would be between 0.8 and 1.5. We call it extreme. Don't be alarmed by this naming, but between 1.5 and 3, the CL is very, very big. So you have very big risk of flow separation. and you probably need some slots. We've put 3 as a at the end of the extreme scale, because there's some papers that show you that there's some kind of section that you can achieve 3, but then it's really hard, and then above 3 it's almost impossible with regular geometries to generate this kind of lift. So with this condition we have here, with this velocity, with this chord, and with this surface, if we want to generate 7.65 tons of lift, we will be at a CL of 0.34. Just remember it as a value. Then we have the Reynolds number. The Reynolds number is the number that gives us a relationship between the viscous forces and the inertia forces. So that's maybe a bit complex, but if you have a low Reynolds, you will be like going through honey, something very viscous. If you have very high Reynolds, you will be going through a fluid that is don't have that much viscosity. And what that is telling us, it's very important in terms of drag calculation, because the more viscous the fluid will be, the more laminarity we'll have around our section. And again, here we've just put a scale. So here we will be at 6.9 millions. And then the Mach number, I'm not gonna get it into here, because in seawater we don't, at least in our foils for the America's Cup, we're very far from having any kind of Mach number that will impact our calculations. So in the America's Cup, more or less, we go between while sailing and not taking off. Then we'll have a look at the takeoff. But between almost 50 knots, it will be a CL of 1.7, and then the lowest value will be 20 knots. That will be 1.06. And then we have to generate the lift, but also a little bit the side force. So we'll have a total force that we'll have to generate, yes, 6.75, maybe 8, something like that. So let's take an average value of the speed, 30, 33, something like that. So let's take this TL. So what we want to do is to generate a section that has a very low drag with this CL of 0.41, let's say. So we're going to go here to our foil sections, and this is a NACA 0012. We have other tutorials where we show you generating NACAs and this kind of, it's a type of section, a type of section parametrization, and it's very common. This is the NACA 0012. So here we can run a polar. So I'm not going to get into all these values. We're just going to calculate alpha CL. Okay, this is a plot of alpha CL. This means how much the CL evolves when we change the angle of attack. So normally the bigger the angle of attack, the more lift you will generate. And this is how the CL the drag changes over the CL. So when the CL is very low, we have very low drag. And when the CL starts growing, you start increasing the drag. So let's call this foil section NACA 12. We're going to copy it. And we're going to try to design our, let's call it super section. Okay. So these are control points. So we can start dragging the control points, and we'll see if we've improved the CL or not. So now where we want to go, this is CL 0.2, 0.4. So we said in this line, we want to be better than the reference. So let's try to play a little bit with it. We're going to move the control points. And look, here we've improved a lot the drag of the sections. Here around 0.4. So, well, I've been playing this for a long time. So I'm going to move it to somewhere that's more or less correct. And you see, while dragging the control points, you have a direct results of the polar of the section. So we're going to try to improve it a little bit more. We're going to show here the curvatures to be sure we have a smooth section. Now I'm going to hide the NACA here just to have a look at the section. Look, it's pretty nice. We're going to make it a bit more laminar like that. And look at that. We're trying to push a little bit more the best of the section here at 0.4. So that looks like a pretty nice section. The best, you know, what we're trying to do is that the minimal drag is just at the 0.4, which is our sailing condition. So look at that. That's a big improvement. If we put it in relative, actually in relative with the ratio, we will improve 25% the drag of the section compared to the NACA. It's not something, the NACA is not thought to be working at 0.4, so it's normal to gain a lot of drag on that. But 25% is a lot. So let's come back here to the absolute change. So you can play with all of these parameters and try to improve the drag. The thing is now, normally the America's Cup boats don't change the angle of attack. What they do change is the flap. They, to be really correct, they change the angle of attack, but mainly when you see them sailing, where the foil trimmer, what he's doing is changing a lot the flap angle. So he controls the right height of the boat with the flap angle, not with the angle of attack of the boat. So normally we're going to consider that the angle of attack is going to remain the same, and we're just going to change the flap angle. So here we have a flap model. If you move the flap, you will see that the flap changes. So here we have a big flap angle, and here we have a negative flap angle. Okay, so now we're going to say here use section flap, and now here, instead of sweeping the angle of attack, we're going to sweep the flap angle. So we're going to tell go from flap -7 to flap, I don't know, something like that, 8, and run a polar of 20 points. If you see still here, I'm going to put back here 0 just to see the section of the shape. If you see here, we didn't change the angle of attack, we are at 0, but still this section is pretty good in terms of flap angle. So let's say we're happy, and this is the section that we've designed by hand. But of course, maybe there's a better section than that. And how are we able to find the best section for this condition? What we do is what we call optimize the section. What does optimize mean? Is we're gonna tell the computer we want the best section as possible at this CL, and you're gonna move the control point along. I'm gonna let you all the freedom to move the control points. So how are we gonna do that? We're gonna add here an optimization. So we're gonna try to beat our super section. Okay, and now here we have a nice visualization of the two sections. So what the optimizer basically is going to do is going to move these control points around these squares and try to find the best section that's going to be the best with the constraints we're going to give him. So, I mean, as a simple view, this box seems a bit too constraining, so we're going to make them a bit bigger here. And then we're going to look at the parameters. We're not going to look today at the bonding sections. We have other tutorials to show you how to work on that. We're going to just focus on optimizing this America's Cup foil section. We, of course, don't need the section to be symmetric, but if you were to design a rudder section, it has to be symmetric because the rudder has to work symmetrically in both conditions. So you would press here in the symmetric button. The bounds, we've already set them. Optimize flap, we're going to let them for later that. Then the trailing edge thickness. The trailing edge thickness is always the same. The smaller it is, the better performance you have, the less drag you have. So we've removed these parameters from the optimization and you put it as a value. We're going to say it's going to be 0.1% of the core of the section. Then this parameter is if you want curvature continuity on the leading edge. So these parameterizations, as it is forced to have tangency on the leading edge, but if on top of that you want curvature, you should click on this. We're going to let it like this for now. Then the maximum number of iterations, the tolerance, where you want so the bigger the tolerance, it will consider it has converged earlier, and the smaller the tolerance, it will continue until more time. Then what fluid we have, so we're going to say it's water. And then the elevation, so that's important for air to calculate some fluid properties, and in water to calculate cavitation properties. So here, let's say we're going to consider it's going to be at 0.5 meter depth. Okay. So we're all set. Now we just have to give him the objectives. So what objective do we have? We want, let's call it, objective one. We want the minimum CD, the minimum drag. The weight is if you have several optimization objectives, which one will be more important? These weights will going to help you to, the more weight you have, the more important it will be for the optimization. The Reynolds number. So here we're going to come back to our fluid calculation. We said it's 6.5 million. So we're going to put it exactly like that, because it's in millions. Then the alpha, we said we're going to let it 0. The flap, I'm just going to explain it to you. We're going to let it 0. And the encrypt, this will make a single video just with encrypt. The encrypt is a parameter that will help you to tweak a little bit the laminarity on the foil. So the Reynolds itself has a big impact on laminarity, but depending on the water chemical properties, depending on a lot of things happening on the water, if the water is super calm, if the water has some turbulence, laminarity can be triggered before or after. So this parameter encrypt help you to tweak this laminarity. So the bigger the encrypt will be, the more laminarity you have. The smaller this encrypt will be, the less laminarity you will have. So here we're going to put, let's say, 0.2. And now, okay, so I have this case with this Reynolds, with this alpha, this flap, this encrypt, and I don't want it at this alpha and this flap. I want you, optimizer, to target a CL of 0.4. This is the CL we've decided we're going to optimize it for. And we're going to try to match this CL with the flap. So we're going to put flap here. And that's it. We've defined our optimization. So now the only thing that we have to do is press the run optimization button. You will see this little status will change in blue. And I'm not going to make you wait. This will more or less take something like 1 minute. So I'm going to cut a little bit this video and I'll come back when we have this minute passed. Okay, so that's the first result. That's a pretty weird section. I've just changed the max number of iterations just to go, because it was really making a really thin plate. And at least this we have a little bit of thickness of the section. But why the optimizer is doing that? Because thin sections have very low drag. If you see here, we already gained a lot in CD with the super section we made by hand. Look at all we've gained in terms of drag. That's a massive gain. But this has absolutely no sense because this section will never sustain the loads of the foil. So how can we say the optimizer A? Okay, optimize the section, but do a realistic section. So we're gonna do that with the constraints. In this case, we're gonna add, let's put 100 iterations again here. Let's add a geometrical constraint that we're gonna call structure. Structure. Okay. Here you have a lot of variables that you can constrain your section with. We have a specific tutorial on that, so we're not going to be too long on that. In terms of stress, the one we're going to use is the section modulus. It's the parameters that will define two sections with the same section modulus will be able to sustain the same loads. So we're going to say have at least the same section modulus as the reference. We can put a value that will come back later into this video, but for the moment just be higher than the reference one, so it will be able to sustain the same loads as the red one. We're gonna run the optimizer again. So that's a weird result. Have a look at that. Look at this section, the shape it has. But hey, look at that. Look how the optimizer go really to minimize this 0.4 CL section. Pretty amazing, huh? But again, this section is pretty weird, and it's pretty weird because of two reasons. Let's start with the simple one. The first one is because always the optimizer will try to minimize the trailing edge thickness, but also will try to go inboard, minimizing the trailing edge thickness. So what we're going to tell him is that this cannot be manufacturable. So we're going to add another constraint. So we have some kind of thickness here in this zone. So here more or less it's like 90% of the section, of the chord of the section. So let's add a new constraint. We're going to call it trailing edge constraint. And here it's get local T over C. And he says XC is the adimensional chord, so between 0 and 1. Let's say the adimensional chord at 0.92, somewhere around here, has to be bigger than the reference one. And we're going to be gentle. We're going to be the reference one, but you can go up to 0.8 times, so 80% of the reference. You don't have to, if you want to be more aggressive, let it be, but at least 0.8. So here we're going to have a bit more thickness. And now the other one is, so let us study, okay, now we have this section. I'm going to show you how to have a little study at this section. So we're going to save the optimized section, and it's going to appear here. Okay, so we're going to be able to make all the calculations that we were making before. So first of all, look at these curvatures, how they evolve along the chord. They're very bumpy, okay? So we're gonna come back here, and we're gonna give him another constraint, which is called the wiggliness. It's a pretty weird name, but I think it's understandable. We're gonna call it wig. We can put whatever name we want, and we're not gonna allow this section to be more wiggliness. It has to be lower than the reference one. So you cannot do this kind of strange things. We're gonna constrain with aerodynamic constraints because this has a huge gradient recovery and can trigger separation. So we're gonna constrain this with, let's say, real aerodynamic reasons, but for the moment we're going to use this parameter because I think it's pretty interesting. And we're going to optimize again, so let's go. So here you see, that's the new section. That was section 2. Look at where it was going here on all this zone. Now with section 3, we are a bit less wiggly, and we've increased the trailing edge thickness. So it's a good one. let's generate the plots to see where it goes. Again, you see how much it lowers the CL here. But of course, again, here we don't like, this is a very aggressive shape, okay? And here we will have separation. Again, let's come back to this one. Here we can run section data. So let's run a single flap angle with just this section. Section data. So here you see that's negative, so that's suction. All this zone is suction on the upper part of the section. So the red is the upper part, the green is the lower part. We have a very big peak of suction here, and then a very steep recovery. You see, that's the laminarity up to where it goes. So he wants to push laminarity as aft as possible. But this huge gradient recovery is too aggressive and will probably have, or at least will have a very big risk of separation in this zone. So how can we constrain this not to be as hard as this? We're going to come back to the optimization. And now we're not going to constrain it with geometry, but we're going to constrain it with aerodynamic constraints. So what we're going to say is, here you have, I'm going to call it top gradient. So we're going to skip this for the moment. We're going to just define the case. So it will be just the same case at alpha 0, flap 0, and grid 0.2. At target CL 0.4 and solve for flap. So in this case, what do we want to constrain? Because we want to constrain the gradient recovery. So the gradient recovery is the delta of the delta of the CP, the differential of the CP, so the derivative of the CP. So we want to constrain it from 0.25%. So the max stops recovery has to be lower than the reference one. Okay. For this, as you can take a reference section, you can take a section that you know it doesn't have separation, and you can just constrain it with that. And now the good thing is, when you define this, you can generate the plots, and you have not only the objective plots, but you have also the constraint plots. So as you see here, we have our optimized section has more gradient recovery than the reference one. So again, let's run optimization and let's see where it goes. So here we are with the new results. Again, we can compare with the previous one. So you see it has moved a little bit, and if we see our recovery, it is below the one we've set to him. Here in results, you can see how much we're gaining. We're gaining 8% of drag, and all the constraints that we've set to the foil, to the section, sorry. So now we're going to have a little analysis on this section. So let's save optimize section. So we're here with it. We're going to hide this one, and we're going to compare it with the super section. And what we can see really quick is that in terms of polar, when we want to generate high CLs, so for example for takeoff or for this kind of low speed maneuvers, we're going to be in trouble because the section is going to separate. So what we're going to say is, okay, I want to be as optimal as possible, but I don't want to lose my properties in terms of high CL. So we're going to come back to optimization, and we're going to add a new constraint, which we're going to call it low speed. Okay, so So we're gonna low speed. Let's go to fluid calculation again. So for example, for takeoff at 18 knots, 1.37. Okay. Maybe it's a bit too constrained, but let's see where it goes. So at CL of 1.27, we're gonna make it with alpha because we can try to make it with alpha. We just want to generate high CL. What Reynolds? 3.5 millions. 3.5 millions. And how are we going to constrain this? We're going to tell him the drag, when you have separation, the drag becomes completely crazy. So we want to limit the drag. So the drag of the section has to be less than the reference one. So if we generate some plots, we see here that the drag is bigger than the reference one at this point. So with this, we will want to move this point down here to have the same properties as the reference one. So again, let's run optimization. So here we go. That starts to be a bit smoother. Let's generate the plots to see where we are at. So we still have a massive gain in drag. And here, now the CD is a bit more controlled. Okay, so we start to have a section that some kind of have a decent shape. Then what happened in the Americas Cup is that the foils have cavitation properties. They have to limit as much as possible the cavitation when they're going at high speed. We have a specific tutorial focusing on cavitation, so we're not going to extend too much on that, but you have the possibilities to constrain also in terms of cavitation. So what the program will tell you is when cavitation starts, okay? Then you can allow yourself to have a bit more cavitation before you have a huge amount of drag. But here what we're gonna do is start limiting when the cavitation will start. So we're gonna add a new constraint. And we're gonna say, so now we're gonna come here and we're gonna limit the cavitation, for example, at 43 knots. As an example, each one, then we can play a little bit with this parameter. So what is the CL we have in this condition? 0.24. So we're going to call it cavitation at 0.24 with the flap. The Reynolds is 0.484 millions. There you go. And what we do want to have is that the inception speed, inception is when cavitation starts to be triggered, has to be lower than a certain value, which is going to be 43 knots. So the inception has to be higher in this case, than 43 knots. Let's generate the plot to have an idea on how this works. So here we have the inception speed. What does this graph mean? We have the CL here varying, and here is the inception speed. This line is marking when the cavitation is happening. So when we are at CL 0.20, what we say here, 0.24, this green foil will be cavitating since 34 knots. So we want to push this cavitation limit up to really high here. So now again, let's run optimization and let's see where we go. Okay, so here we go. That section starts to be pretty different again. Let's have a look at the results. Oh, there's a lot of red here. So we already lost a lot of drag, the wiggliness, and then the inception speed. So we've improved, if we generate the plots here, we've improved a lot the cavitation, but already we are losing in terms of drag and we're struggling. So already this section was very far from our cavitation limits, and he almost got there to the 43 knots, but he didn't achieve to do it. So let's just have a look at this section, save it, and we're going to see its properties. So here we have all the properties of the section. So we have here the section modulus, and here the thickness, 12 point something. So maybe the thing is, the bigger the thickness of the sections, the lower the cavitation properties. So let's make some numbers to see if this section modulus or this thickness has some sense or not. We have this beam calculation that will help us to define 95%, or maybe not that much, 80% of the most common ways to calculate a wing. So in general, a wing can be considered as a clamped beam sustaining some forces. So in this case, the wing of the foil has two sides, so it's calculated on one side because in the America's Cup the foil had to be completely symmetric. So on one side of the beam we have half a wing, and on the other side the other half, and here we're just looking at half of the wing. So here we're going to have a certain load on the wing. Let's start with the elliptical. This is how the force is going to be distributed along the wing. In theory, the elliptical wing is the best distribution of pressure along the wing that gives the smallest induced drag. Bit of technical terms here, but in general we will try to push a little bit for this kind of elliptical shape of the lift distribution. So the span of the foils are 4.5 meters. So the half span, which is what we're showing here, is 2.25. The chord, let's take 0.4, because normally we're going to look for a section that is close to the root. And the total force, so that's a big topic. In principle, the force that the foil has to lift is 7.6 tons, something like that. And this will be the two wings. What happens that when you try to remove some foil of the water, because the less foil you have on the water, the less drag you have, the less wetted surface in general is less drag. So you try to push the foil out. The outboard wing is gonna start little by little to be out of the water, and all the load is gonna be to the inboard wing. So the inboard wing is gonna have to sustain a huge amount of load. So you could consider maybe not the full lift of the boat, but maybe let's consider the inboard wing will take 7 tons, something like that. And then here's another topic, is how much stress do you allow to have on your wing? In this case, in the America's Cup, we had in general steel foils. We're going to simplify it a lot here, and we're going to consider it's completely full of steel, and all the steel is taking part of sustaining the forces of the foil. So how much stress will we allow on this wing will depend on the material. The rule of the America's Cup tells us that the maximum yield stress of the steels has to be 1,500 megapascal. We have to take some safety margins, and this is how much safety margin you want to take is where you're going to put this number. You also have to take into consideration that you have some fatigue loads, and so this number, now we're going to put it randomly, but this number is pretty important. Let's take from 1500, let's say we allow to have 1000 maximum stress on the wing. And the good thing is that this, first of all, we'll see here how is the bending moment diagram on our wing. The bending moment is directly linked to the stress you will have on the wing. We're going to decide the more you're at the tip, the less bending moment you have. The more you're at the root, the more bending moment you have. So somewhere here, more or less. The bending moment is 5.7 tons meter. And the section modulus is this value. The thing is now with the chord we have, we're going to non-dimensionalize this section modulus, and this is the value we'll have here. So we have 885, which 885 multiplied by 10 minus 6. So here you have a little thing to directly copy, and when you copy it, you can directly put it as a constraint in the optimization. So now you're going to go to optimization, and we're not going to say to be higher than the reference one, but to be higher than the value we've calculated. Okay, just by curiosity, we're going to see what was the section modulus of our super section. So the section modulus of our super section was already pretty high. So let's just put the same value we had here, which is how much? 885. So to be fair with our super section, we're gonna also put the same section modulus here, 885. You see, well, here it has target to have 885 with the thickness. So we've reduced the thickness a lot. So now we're gonna be fair in the comparison. Let's come back to the optimization. And now, just by curiosity, we're gonna generate the plots, and we're gonna see the cavitation constraint. Already our reference was pretty lower than that, so our reference has grown a lot in terms of cavitation. So we should expect now to be able to pass this cavitation constraint. So again, let's run the optimization. Let's see where we go. Okay, look at this section. We're starting to have nice cavitation properties. Still a bit low compared to the constraint we've inputted, but probably with a bit more iteration he will converge to something that's passing the cavitation constraint. So now, what happens when you look at the drag? It looks to be very picky to the exact point of the CL, but then in the C you have a lot of angle of attack change, you have waves, and the conditions are not perfect. So we can also play a little bit with that, with this little checkbox. We can say, okay, that's the condition we've optimized it for 0.4, but I want to have a look around -1 and +1 degrees around this condition. And you're going to make 3 points again. You're going to make the condition point, +1 degree and -degree. And I want you to optimize in this range. And also, as this, for example, NQuit value is a bit, say, sometimes arbitrary, we also will want to play around, and we're going to say, I want to be around 0.1 and 0.5 with 3 points also. So we'll have some kind of a robustness around our optimization. We're not optimizing in a single point, but a little bit around this optimal condition. So let's see where we go with it. So here's the new section. Let's see how it has changed from this one to this one. Has removed a little bit of camber. Let's see the plots. So we start to pay a lot due to this cavitation constraint. What else do we have here? But look at that. Look how high we are now in cavitation, huh? I'm sure now we are correct in cavitation. Okay. Oh, and here we have a little bit of recovery. The recovery is a bit higher than the gradients than the reference one. Actually, these values seem acceptable. We could be a bit more aggressive on that. I'm sure the section we've defined when we've optimized ourselves, let's say by hand, was already pretty nice in terms of recovery. So we could allow, let's say, a higher value than that. Let's put, I don't know, just in case it's something that is disturbing him, the top gradient, let's put it inferior to 4, for example. Okay, nice. And now another parameter that we can play with. So first of all, let's define another kind of flap. So here we have this kind of kinky flaps. Okay, but in terms of aerodynamic results, it gives some peaks, and so we're gonna define some kind of a smooth flaps that when you deflect, it's let me hide the other section so you can really understand well what I'm saying. You know, you have a smooth transition and you don't have a super close hinge. Let's put something like that, even a bit more, so it's really smooth. Okay. Okay, I'm gonna make the same to the initial section NACA. So it will take the same flap as the initial one. So let's put this one and 0.4. There you go, 0.4. So the next one that will be optimized will have also this hinge. But now, what we haven't played with is with the hinge position. So where will the hinge go if we say, now optimize the flap? So let's have a look. Run optimization, 1 minute, and we're back. So nice. So here we are. Look at where the hinge has gone, to the middle of the chord. So the optimizer tried to increase a lot the size of the flap. So yeah, that's interesting. The limitation of that is that as the flap has a huge surface now, it will have a huge amount of loads that some actuation will have to sustain these loads and to push against these loads. So that will be the limiting factor of it. So for the moment, we're going to remove the optimization of the flap, and we're going to start to just play around with some parameters. Let's see up to where we go. We're going to first remove this wiggliness parameter, because currently the section is pretty smooth, so the less constraints we have to focus on our objective, the better it will be. The trailing edge, honestly, here it's already decently thick, so I think we can be a bit more challenging on that. That's the cool part, where you start trying to play a little bit with where you could press a little bit to gain a little bit of performance. And then, for example, the low speed, let's relax it a little bit. So instead of going up to 1.3, let's go to 1.2 of CL, which is already a decent CL. And where we could gain a little bit more on the structure, Okay, let's remove a little bit. Let's let it to 800. Okay, let's challenge a little bit. Let's see where we go. Already this section looks pretty cool, huh? But 800, would it mean that we allow ourselves to go to 1100, which is a lot, really. But anyway, it's just to play. It's just paper. Nothing's gonna be wrong here. Okay. So yeah, let's play a little bit with that, and let's see where we go. So here we go. Here we go. That's the new section, and here are the results. So we are even in drag, and we've passed all the constraints. So from here you've seen all what you need to play with all the parameters as much as you want, and to find a final section that you're happy with. Actually, this one, I like it decently. I'm gonna save it here. Let's call it Opti AC75. Let's hide the other ones. That was the reference one. Let's put it in green. There we go. Yeah, looks nice. And now what we do with this, we just need to export Opti AC75 and export it to, you can export it to the DAT file. That is the point ones. You can export it to Geo. That's the format to then mesh for Gmesh. But usually, if you're gonna input it in some kind of a CAD model or to design a foil with it, you just export it to IGES, and you'll have an Opti section that you can open in Rhino or whatever file. So yeah, that's a bit the end of the video. I hope you like it, that you learn something. We let you hear down the link of the application. You can, there's a free layer, you can do huge amount of things with it, and you can play with it and start learning or use it as you want. And we'll upload more videos on designing an AC75, designing the 3D shapes of the foil, designing the hull, and designing other parts of the boat. We'll also prepare some videos on optimizing sections for other kind of foils or aircraft. And yeah, so please, we're super happy to know all your comments, what you think about it, if you want us to upload other kinds of videos. And we hope a lot you liked the video, that you learned something, and yeah, just subscribe, and hope to see you on the next video. Thank you.